Okay, so today we're going to kind of continue down the rabbit hole. And one thing I would actually stress to kind of keep in your head, I mentioned in a lot of my classes, those of you who've had me before will recognize this. A lot of the things we do are the same. The terminology and the notation may change, but the ideas and the principles are the same. We define linear transformations, and we said that linear transformations are essentially functions. They're defined slightly differently, but essentially we can think about them as being analogous to functions, which means now we want to take all of maybe the things we know about functions and see if they translate to linear transformations. First, though, before we get there are some benefits to using a linear transformation, and in particular, how we write out our linear transformation that we'll see, and then we'll kind of start going through what we want to go through today. But the idea is we have a linear transformation, and we'll just have one going from R3 to R3, and suppose we have this. T of x sub 1, x sub 2, x sub 3 is equal to, which one do I go with? 2x sub 1 plus x sub 2 minus x sub 3, or negative x sub 1 plus 3x sub 2 minus 2x sub 3, and 3x sub 2 plus 4x sub 3, which is one way we wrote out our linear transformation, essentially in function notation, but because this is an R3, we essentially have to write the function 3 times, once for each dimension. Those of you who have already taken Calc 3 will kind of recognize this when we have to kind of write out what happens in each dimension. And it can get really cumbersome really quickly. But as linear algebra, we spent a lot of time working with functions, and we understand that I can also write linear transformations as matrices, where we had the definition, T of x is just equal to AX. And now we can write this like this. Let's see, 2, 1, negative 1, negative 1, 3, negative 2, 0, 3, 4. And we're going to check just to make sure I'm not really going. Yep, there we go. Times x sub 1, x sub 2, x sub 3. And now if I let this be my A, this is just my x. This is AX. And if I multiplied all of this out, I would get this. All I'm actually doing here is the first row here, x sub 1, x sub 2, x sub 3, I just find the coefficients. 2, 1, negative 1. Second entry, second row, negative 1, 3, negative 2, etc., etc. And it gives me a nice way to write out my matrix A. And all things being equal, this is actually a nicer, neater way to write out a linear transformation than to write all of that out. Which means now we want to get used to writing linear transformations this way, not this way. Or if it's written out in this form, to be able to rewrite it in this form here. Because then all of my operations on matrices kind of come into play, and then I'm really just reviewing stuff I already know, because I'm just working with matrices again. The problem maybe? Well, for an arbitrary linear transformation, how do I figure out what the matrix A is? Will this trick always work, where I can just look at the coefficients here and that will dictate what my matrix A is? And as it turns out, that is not always true. It is true here for a specific reason, which we'll see in a second. But then maybe that will lead ultimately to the question of when is it not true, and we'll kind of see what happens there. But assuming I have an arbitrary linear transformation, the way to figure out what my matrix A will look like is to see what the linear transformation does to the standard basis in whatever vector space I'm talking about. Because if I can figure out what it does to the standard basis, then I can use my understanding of bases and transformations of bases to then figure out what will happen to everything in that vector space. So we understand, say if we're in Rn, we know my standard basis, we also have my standard basis vectors, and just because I don't think I've officially written it this way, your book kind of jumps between notations. We actually write the standard basis as E sub 1, E sub 2 out to E sub n for an n-dimensional vector space. And in this case, E sub 1 is just equal to the column vector 1 and then zeros everywhere. E sub 2 is 0, 1, and then zeros everywhere else, etc., etc., etc. We're used to writing them this way. This is kind of the shorthand way of writing them with E sub 1, E sub 2, E sub whatever. Okay, but then what I do is I have my basis and my basis vectors. I have my transformation. Again, we'll go Rn to Rn. Then we'll look at that one again maybe. And essentially, I need to figure out what the transformation does to these basis vectors. So really, I need T of E sub 1, which we'll just call A sub 1 down to A mn, M1, this is the first column. But then I need T of E sub 2, which I'll just call A21 down to A M2, etc., 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 for all n of those all of those basis vectors. And yes, essentially what I'm saying is I have some arbitrary transformation and I don't know what it is. And I'm going to use that transformation on these basis vectors and get some column vector with a bunch of arbitrary things that I don't know what they are. Which is really, really kind of arbitrary. But the idea is then, once I have all of these columns, I can create a matrix A using these columns. A11 out to AN1, AM1 out to ANN. And now I can just define this A as T of V equals AV for all vectors in my vector space, for all V in V. And we call this the standard matrix. And again, I would say yes. So essentially I'm saying, okay, I have an arbitrary transformation and I apply it to my basis vectors to get arbitrary column vectors, which I then write as a matrix, and then I call that the standard matrix. But we'll actually see, once you see an example, we can see how this works and why this is a good way to do this and beneficial, and then we'll expand on it from there. So let's see. Well, we could actually use this one right here. Yeah, we're running out of room, but since we have that right there, what I need to do is, I need to find T, for this T right here, I need to find T of E sub 1, and then E sub 2 and E sub 3, because this is in R3 right here. So let's see, T of E sub 1, E sub 1, again, is just 1, 0, 0. So in this case, X sub 1 would be 1, then 0, 0. So this would just give me 2 in the first entry. Then in the second entry, negative 1. And then in the third entry, there's no X sub 1, which would be the only 1, so to speak. Those would both be 0. So that would be 0. And again, all I'm doing is saying, for the standard basis, E sub 1, this is 1, 0, 0. And then I'm just plugging in. X1 is 1, X2 and X3 is 0, and seeing what I get. Do the same for E sub 2 and E sub 3. For e sub 2, now those are 0, this is 1, so all I really care about is the x2 entries. That's a 1. That's a 3. That's a 3. Then I get t of e sub 3. And again, now all I care about is x sub 3. That's a negative 1. That's a negative 2. That's a 4. Now I have my e sub i's. Now I rewrite those as column vectors in my matrix. So my A should then equal, this is the first column, 2, negative 1, 0, 1, 3, 3, negative 1, negative 2, 4. And that should be the A that represents my transformation as a matrix. But if we look, that's actually the exact same thing we got here. Which means it really gives us two different ways to find this standard matrix, assuming we are using the standard basis, which for this in R3 we clearly are. One way to do it is to find how the transformation affects all of the vectors in your standard basis, and then write those out as column vectors to form a matrix. The alternative way is to kind of read it row by row by row, and if you do it correct, you should get the exact same thing. Again, the ultimate question here is, what happens if we decide to use a non-standard basis? How does that change this? That comes later. Okay, but first, just to maybe do one more to make sure we're clear on this. Let's see. Suppose I have t of x, y, z. We'll go R3 to R2 this time. And it's equal to x minus 2y, 2x plus y. And I want to find the matrix A. There's two ways to go. One, again, is to write this term by term using the rows. The other way is to use the standard basis. Keep in mind here, we're going from R3 to R2. My basis is in R3. So here, we'll use the bases, and I'll need E1 to E3. So I need T of E1, T of E2, and T of E3. Here, X is 1, Y and Z are 0. So I get 1, 2. Here, Y is 1, X and Z are 0. So I get negative 2, 1. Here, Z is 1, X and Y are 0. I get 0, 0. Now, I write these as column vectors, and I get 1, 2, negative 2, 1, 0, 0. And this is my matrix A. The one issue here maybe, if I choose to do this the other way, using my rows, we just have to keep in mind, since I'm going to R2, there is no Z represented here, because it's going to become 0, but I still need to account for that over here. So here, these are both in R3, so I would get 1, Y is negative 2, there's no Z, so it's 0. Here, X is 2, Y is 1, Z is not listed, so it's 0. And you end up with the same matrix, as long as you keep in mind, this is in R3, so this has 3 entries in the row, even though these only have 2. Ultimately, you all understand how this works. in theory, will I sometimes say, find the matrix A by way of the operation on the standard basis? Maybe. Or I'll say, find it however you want and just get the matrix A. Ultimately, it's just different tricks that allow us to solve it. And again, you kind of understand how this works. More than likely, we'll start doing this with non-standard bases, and then I'll make you do all the work out because it requires more work. Okay, but let's see. That's enough examples of that, I think. So let's see then. Now, I have a linear transformation, which I understand is kind of, sort of, essentially a function. Only now, instead of writing out my function, say, algebraically, I'm going to write out my function, my linear transformation, as a matrix. But it still represents a function, so to speak, a linear transformation. So what else can I do with functions? A standard trick with functions is composition of functions. Once you have a few functions, you compose them together. Well, now I have linear transformations that I'm going to represent with matrices. Can I find the composition of linear transformations? All of you understand how composition of functions work. It takes you from here to here, and then here to here. Well, now I can kind of just call these things vector spaces, and basically I can start in, say, R3, use a linear transformation, maybe we'll stay in R3, then create another linear transformation to go over to R3, and the composition just starts in R3 and ends in R3. So it's the exact same idea, only when you heard about this in pre-calc, calculus, whatever, you're talking about functions and domains and ranges. Here, now we can talk about linear transformations, domains and ranges and codomains and things, and images and pre-images and things like that. But in principle, it's still the same idea. So, suppose that T sub 1 maps Rn to Rm, and T sub 2 maps Rm to Rp. And keep in mind, those could be the same dimensions, they could be different. These definitely are going to have to be the same, because that's kind of the middle space that you're talking about. So it has to be the same for both of them to make this all work out. Okay, given that we define T as the composition T2 composed with T sub 1, which goes from, we understand how this works, I apply this one first, then that one. So I do T1 first, so it starts in Rn, which then sends it to Rm, and then T2 sends Rm to Rp. So the composition goes Rn to Rp. And yes, keep in mind, just like with functions, I could also do T sub 1 composed with T sub 2, which would go Rp to Rn. We go backwards. Once we have this idea of composition, we understand I can compose in lots of different ways. Here we just want to kind of work through this a little to make sure we understand what's going on from a matrix perspective. So, let T sub 1 map Rn to Rm. I have to rewrite what I just wrote. T sub 2 map Rm to Rp. Be linear transformations. The composition T equal to T sub 2 composed with T sub 1, defined by T of V is T sub 2 of T sub 1 of V, our regular algebraic way of writing out my composition, is a linear transformation, and the standard matrix A is equal to A sub 2 times A sub 1. As far as a proof here, This is really just properties of the linear, apply the properties of the linear transformation here, and apply properties of matrices here. So the proof is really straightforward and simple. It's like 2 or 3 lines. You can all do that out. But again, what it means from my perspective, now I can define a couple of linear transformations written as matrices, and in order to understand what that linear transformation is doing, I need to find the standard matrix. And in order to find the standard matrix here, I just find the standard matrices of each of the functions that I'm given and multiply them together. Keeping in mind, order matters here. We know matrix multiplication is commutative, so make sure you do these in the correct order. Okay, good. So, to kind of work through it, let's see. Suppose we have t sub 1 of xyz is equal to x plus y, 0, 2x plus z, and t sub 2 of xyz is equal to x, z, 2y. These are linear transformations, and we'll go from R3 to R3. I want to find the standard matrix for the composition T, which is equal to T sub 2 composed with T sub 1. And again, I do stress standard will be T sub 2 composed with T sub 1 because you apply T sub 1 first and then T sub 2. But you understand you can do this in different orders. So just make sure you read and pay attention carefully. Okay. Well then let's see, what do I need? I need to find a sub 2 and a sub 1. And in this case, I'm actually going to do them backwards because I know a is equal to a sub 2 times a sub 1. So find a sub 2. And here, I'll just use my understanding of the transformation rather than finding it by way of the standard basis vectors. So that will be x is 1, and then y and z will be 0. Second entry, x and y are 0, z is 1. Then I get 0, 2, 0. So there's my a sub 2. A sub 1, up there, I will get x plus y, and then there's no z. The second entry is always 0, so that row is just 0. The third entry is 2x, no y, and z. Now, multiply those together, which you all know how to do, so I won't take the time to write it out, work through it here. But we get 1, 1, 0, 2, 0, 1, 0, 0, 0. And this is my standard matrix A. Telemarketers calling while I'm making videos. Okay, good. Which means now we have a trick. I can define linear transformations, several of them. Here I only define 2, but we kind of get how this works. I could define 6 linear transformations, and I could compose all of them together. And then, to find the standard matrix for the whole composition, I would just multiply the standard matrix for each of those 6 transformations together, just making sure I kept the order correct. And again, it should be obvious at this point, yes, there's this new definition, the standard matrix composition of a linear transformation by way of matrix representation. But it's really just all the stuff we've been doing the entire semester. We're just giving a name to it. But, again, all of you kind of understand where this is going. And this is where I was discussing this with my wife yesterday and pointing out. It really upsets me that we have to do this class online because there are some things that I think work better sitting in a classroom and just saying, what do you think about that? So I'm actually going to go through one more thing, and then I'm going to leave the last little bit of this section for you to read through and ponder on your own, because if this class was actually seated, that is exactly what I would do. I would say, we thought about this, now what do you think is going on? And in the seated class, I would just let you sit there and work through some problems and kind of ponder it to get an idea of what's going to happen. So I'm going to do the same thing here. But, well, functions, linear transformations, composition of functions, composition of linear transformations, the natural follow-up once you define composition of functions is to say, is there a function that will undo the function I started with? Ergo, if f goes from here to here, is there some function I can compose it with that sends me back to where I started? And you all say, this was the thing we would discuss if it was a seated class, you all say, yes, it's the inverse, the function that undoes what I started with. Well, now I have a matrix representation of a linear transformation that takes vectors here and sends them here, and the natural follow-up is, can I find a linear transformation that goes from here to here? It undoes what my transformation did. And I would point out, now that we have an idea of composition, it seems logical that that should occur. I should be able to find a linear transformation that does the opposite of what the original transformation I had did. We understand there is going to be a little bit more attention to detail here, because now I'm talking about vector spaces, and if I'm going to go from here to here to here, I have to make sure that my mappings line up in such a way that everything gets taken into account to make sure there aren't random vectors floating around that don't get inverted correctly or things like that, which we'll see in a second. But if I think about it, we have this matrix notation here, and well, essentially I'm defining a linear transformation as AV, where this is my standard matrix. And it should be obvious that if I wanted to compose this with another transformation, with another standard matrix, well, if I just chose A inverse as that matrix, then these two composed together would undo each other, and I would end up back where I started at V. So it should be obvious that this is possible, and it's one of the, we'll say, uses of writing this as matrices, because then I can apply my understanding of matrices and matrix inverses to see what's going on. But again, we have to make sure, just like we kind of did with functions, we have to make sure that this A is invertible. If it's not invertible, then this won't work. So now we'll be restricting ourselves to transformations whose standard matrices are invertible. Or, if it's not invertible, then it just means we can't find an inverse for it. Similar approach to functions. So we just have to kind of make sure to pay attention to all the details. But again, this is essentially algebra, linear algebra, which tells me, oh yeah, I should be able to get this work in certain situations. So another usefulness side effect of writing these things as matrices. But okay, to kind of work through the definitions, to actually formally write the definition, I know you all know it from functions, but if T1 goes Rn to Rn, and T2 goes Rn to Rn, if T sub 2 of T sub 1 of V is equal to V, and T sub 1 of T sub 2 of V is equal to V, then T1 is invertible, and T2 is the inverse. And again, I would point out, kind of like what we were saying, in this case, these are all Rn, I can't have RM and RP and all that because I'm going back and forth. And so these things all have to line up, which means I can't have different size vector spaces because that will cause a problem because this has to work in both directions. T2 composed with T1 and T1 composed with T2. But again, all things being equal, that's just my regular inverse definition. But we do get this. Let T map Rn to Rn be a linear transformation with standard matrix A. Then TFAE, which you all know now means the following are equivalent. 1. T is invertible. 2. T is an isomorphism. And 3. A is invertible. And before we look at this, I would point out, if this is true, then the inverse of the transformation T is T inverse. The inverse of A is A inverse. And the standard matrix for T inverse is A inverse. So there's this natural relationship, which is obvious. But as far as this goes, this is a nice, simple little proof here. This one is actually a homework exercise that I want you to work through. Again, if we were seated here, I would have you work through these in class before we moved on. But if you think about it, the following are equivalent. If T is invertible, then T is an isomorphism. Well, if T is invertible, it means it takes everything here to everything here, and then immediately takes everything here back to here. Because if it's invertible, it has the inverse, which sends me back, which means everything here gets mapped to everything here, which gets mapped to everything back here, which means they have to be the exact same. Because if they're not the exact same, then that will not work. There'll be some connection that doesn't hold up, so to speak. So it's pretty obvious that if T is invertible, it has to be an isomorphism. They have to be the same space. Again, we understand by same, I don't necessarily mean R3 to R3. We saw different types of spaces, but they have to be the same structurally speaking. But let's see. If T is an isomorphism, that means it's a mapping that keeps everything good here, and I have a standard matrix here, and I'll have a standard matrix here, but for A to be invertible, there has to be a matrix I can multiply by to get the inverse, but it should be pretty obvious that I can do that. If it's not, again, like I said, this one I want you to work through. It's actually a homework exercise. It should be pretty straightforward and easy to prove. If there are questions on working through the proof, email me, let me know, and maybe I'll give you until the beginning of next week to work through it, and then I'll, if there are still questions, make a video and kind of walk through it. But this one, you should be able to kind of see the natural connection from A to B to C. And if this is invertible, it clearly leads to that being invertible. That should be straightforward and obvious. Okay, good. But anyway, all of this follows directly and simply, again, from our understanding of functions and composition of functions and inverses. And again, finding my standard matrix is pretty straightforward and simple. We can, all things being equal, just read it off from the transformation I'm given. We did that. The reason that works is because we're using the standard basis and getting the standard basis or the standard matrix from that standard basis. So it's straightforward and simple. The question is, what happens if I start using a non-standard basis? clearly there's going to kind of be some transformational thing going on there to shift from the standard basis to the non-standard basis. We actually did that earlier in this chapter, or it may have been the last chapter, I honestly don't remember. But we did that earlier. So now, can we apply our understanding of how to convert from a standard basis to a non-standard basis and use that to find the basis, the standard matrix, or the non-standard matrix now, for transformation? How does that change? And this is where, like I said in class, I would say, hey, you got a half an hour left, mess around with that and see what you can come up with. It is in your book. It's just a nice, simple little algorithm, similar to what we did to go from standard basis to non-standard basis. And I think you can figure it out and work through it. But again, from a seated class perspective, I would let you work through it so you could ask questions as you went through it if there were any. So I'll do the same thing here. Work through it. If it is a little bit confusing, email me and let me know, and I'll do the same thing. I'll make another video working through a few examples, just like I would do in class. But for now, I'm going to assume that you can work through it and understand it. If there are any questions about any of this, again, feel free to email me and let me know, and I'll make more videos.